Today I'm going to talk about what I believe is a common misunderstanding of the nature of physics and its laws. I do not know when this misconception started, but I see it very present today, sometimes just in the back of the mind. That is that the universe is like a gigantic mechanical clockwork, and the laws of physics describe how it works. They describe how the universe works. And this seems very plausible. You have planets and they move according to some rules. You have electromagnetic radiation and it propagates according to some rules, and it interacts with matter according to some rules, and so on. We imagine these things always happen according to these same rules, no matter what we do. And so we imagine these rules are what govern the universe. They are the laws of the universe, the way that things work. Now, some may think I'm going to object with some quantum mechanical weirdness, so that measurement affects things in a weird way, or that the universe needs an observer. No. The only thing that quantum mechanics changes is the idea that every measurement is an actual physical process, and the effects of this process cannot be made arbitrarily small, so it cannot be neglected. And therefore, these interactions need to be taken into account in our description. Conceptually, it doesn't change the idea that the laws are describing the universe. No, the problem is actually another, and it's easily understood with a few ideas from control theory, which is a beautiful subject. It's a shame most physicists never studied or even seen it. The whole premise of control theory is that you have a system described by a state at each time, a law of evolution that tells you how the state evolves in time, a set of inputs that affect the change of the state at each time, and a set of outputs, variables that you can actually measure. The whole problem of a control is, how can I make the system do what I want given a set of input and of outputs? There are two very important properties of the system, things you want to know about this setup. Can you, with the given output, know the full state of the system? You may think that if your system has n variables, you need at least n outputs. And that is not true, because you know the law of evolution. So for example, if you only measure position over time, you will also be able to reconstruct velocity. This property is called observability. A system is observable if you can reconstruct the state given its outputs. Another question is, can you, with the given inputs, place the system in whatever state you want? If you can, you say the system is controllable. As you can imagine, controllability and observability are two key concepts in control theory. And you want them both. If you have only controllability, say you can accelerate and steer your car, but do not have observability, you don't know where you are and how fast you're going, you're not going to be able to drive where you want. So what does this have to do with physics? Well, the setup of a scientific experiment is, in a way, an exercise in control. The goal is different. In control, we know the law and we use it to achieve a desired outcome. In physics, you don't know the law, you have to figure out what it is. Still, in physics, you need to prepare some states, so the system you study must be at some level controllable, or you can't reliably prepare the states you want. So the system you study must be at some level observable. If you can't prepare the states you want and you can't measure them, you can't really explore the dynamics, and you will have a problem reconstructing the law. Now, suppose you have a system that is not fully controllable or fully observable, but the output is fully controllable given the inputs. That is, you can't fully explore the system, but you can fully explore the part that is observable. In that case, part of the dynamic of the system can be neglected. In engineering, in fact, sometimes you don't even have the state, you just talk about the transfer function which links the inputs to the outputs. That's because the internal may be too complicated to model, or you don't really care about them anyway. The point is, you may have extra state, extra degrees of freedom, but if they don't affect your inputs and your outputs, they don't matter. And here is the main insight. In physics, we never study the full state of the system. Instead, we find situations in which a few variables can be studied independently, unaffected by everything else. We're effectively trying to find dynamics that nicely decouple. This should be clear in classical mechanics, where we study position and momentum of the center of mass of a body without caring what the bonds between all the parts of the body are. In thermodynamics, we study temperature and pressure without caring about all the motion of all the particles. But this type of partial description is there in all settings. When we study atoms, we do not care about the interaction within the nuclei. We can study and manipulate a proton without caring to describe the quarks. While our scientific understanding has grown and found finer and finer description, the process cannot ever hope to encompass the whole state. It will always leave out the unknown unknowns. Do we know that there is no substructure for the electrons, for the quarks? We cannot. Can we know whether there are other forces, other ways that the constituents of the universe interact apart from the ones we know how to measure and manipulate? No, we cannot. So the only things the laws of physics can describe is the part of the universe that we can, under some circumstance, observe and control. They can't do more than that. They can't say what is there or not there. They can't say what truly happens in a way that philosophers would call ontological. They can only describe what is accessible through experimentation. So the laws of physics describe what a part of the universe can tell about some other part of the universe. The laws of physics are not the laws of the universe. So these are my thoughts as of now. I hope they help.